Welcome to the final class of Math 331 problem solving, where we discuss math and nothing but math at the highest plane of existence. All right, so given that this is our last chance as a formal class, I want to talk about differentiating identities. So this is one of my favorite techniques in all of mathematics. Has anybody here seen differentiating identities? Okay, so you either cannot play or you get the really advanced theoretical questions. Deal? Okay, so in mathematics, bread and butter for us is equations, equalities. We love them. They are often a lot of work to prove. Sometimes we don't have equalities, we have inequalities. We've done the arithmetic mean, geometric mean, and a lot of variants of that. One of the most useful equalities we have is the geometric series. So 1 plus x squared equals 1 over 1 minus x. Is this correct?
Well, if x is not too big.
Okay. Let's quantify not too big. We can be very explicit as to what not too big is. Less than 1. There are lots of ways to prove this. Okay? One of the nicest is to look at the finite series, Sn is 1 plus x to the n, then look at n, and multiply by x, you'll get x plus x to the n plus 1. Subtract, you get 1 minus x times Sn is 1 minus x to the n plus 1. So when you divide, you get 1 over 1 minus x minus x to the n plus 1 over 1 minus x. And what's nice is if you write it like this, you have the main term, you have the correction term. You see that as long as the absolute value of x is less than 1, this is going to be really good and small. All right. What if I gave you things related to the geometric series? Would we still have a nice closed form expression? So for instance, imagine I give you, I want the sum, n goes from 0 to infinity, of n x to the n. If we didn't have the n, it would just be the geometric series, and we know how to do this. Now, the geometric series has a truly remarkable, wonderful property. The tail of the geometric series is so if we write 1 plus x to the n plus x to the n plus 1 plus x to the n plus 2, what can you say about the tail?
It's a multiple. Well, it's a geometric series.
It's a geometric series. The tail is just x to the n plus 1 and then 1 over 1 minus x. So for a lot of things with the geometric series, you can actually justify things with a lot less work than for a typical series. Typically, you have to use techniques from analysis to justify switching a derivative and a sum. Whenever you have an infinite sum, there's a problem. I want to be able to take term-by-term derivatives. Well, what's nice is if I write my geometric series like this and note that the tail is itself a geometric series, I now only have a finite sum. I know the derivative of a finite sum is the finite sum of the derivatives. And then I just need to show that this piece goes to 0. So if I take the derivative and I multiply by x, so I'll do x times d by dx. And the reason I'll do x d by dx is when I take the derivative, I'll get an n x to the n minus 1. If I multiply by x, I just keep the power at x. And so the derivative of this piece will just become, 1 becomes 0. This will become 1x plus 2x squared plus n x to the n times x. And now I need to take the derivative of this piece. How do you take the derivative of that piece? Okay, there should not be this long of a pause. How do we take the derivative of this piece? You could do it as the product rule. It's normally phrased as the quotient rule, but yeah, we can use product rule, quotient rule, something like that. We'll get a 1 minus x squared down below. And now you've got to remember, okay, we have f over g. It's f prime g minus fg prime. So we get n plus 1 x to the n minus x to the n plus 1. And then when we take the derivative of this, we'll get a negative 1. So it should be something like that. I don't care what it is exactly. The key thing is, if the absolute value of x is less than 1, both terms will be so small. Doesn't matter what x is, because this is a fixed number down below. This piece is going to tend to 0. And then we can say that in the limit, the derivative of the infinite sum will be the sum of the derivatives. And this is the idea of differentiating identities. You start with an identity, and then you show that you can differentiate it term by term, and it will generate a new identity. So explicitly, we would start with this is equal to 1 over 1 minus x, and then apply x d by dx to both sides. And so when we do that, we now get the sum, and goes from 0 to infinity, of n x to the n. Is now we take the derivative of this side, we have a 1 minus x inverse, we get a negative 1 minus x to the negative 2. Derivative of this is a negative 1, which kills the negative sign. So we get x over 1 minus x squared. So for example, if we take x equals a half, you get the sum, n goes from 0 to infinity, of n over 2 to the n is 1 half over 1 minus a half squared, which is 2. And this allows you to calculate sums like this. Okay. Did I give you the series challenge to bypass induction to evaluate sums? I will do this. This is another route for an A+. I know there's at least one person who is still trying. We shouldn't all look at him at the same time. We should do it in stages, yes.
Wait, sorry. It's x over 1 minus x squared?
Yeah, when you take the derivative of this with respect to x,
Yeah.
and then multiply by x.
Oh, sorry.
Right.
Not,
Yes.
Yeah, okay.
So we multiply by x because it makes things a little bit nicer. This is frequently used in probability to calculate means, variances, moments. It's an extremely useful technique. If there's time at the end of today, I'll give you some examples of how you can use it to calculate moments of various probability distributions. A lot of times the challenge is which calculation is going to be easier, multiplying by x or not multiplying by an x. I'll do one more brief aside, and then we'll shift on to the possible A+. So you want to study the sum, n goes from 0, let's do k. K goes from 0 to n of n choose k, p to the k, 1 minus p to the n minus k. What does this equal? Yes. 1. This is the binomial theorem. This is just equal to 1 plus, I'm sorry, p plus 1 minus p to the n. I might want to study the sum k goes from 0 to n of k, n choose k, p to the k, 1 minus p to the n minus k. This is the probability of a binomial random variable. It's the probability if I have a coin of probability p of getting heads, I have exactly k heads and exactly n minus k tails in n tosses. So this would be the mean. One way you might try to calculate this is, well, I've got an n factorial over k factorial, n minus k factorial. Maybe the k's cancel, and maybe I can play games like this. Once you solve this, you would eventually want to study k squared, so you could start getting the variance. Or you might want to calculate higher moments. Well, the idea is to apply differentiating identities. And you can use that to calculate these sums very quickly. Now, to do that, if I were to apply the derivative with respect to p, the problem here is I've got both a p and a 1 minus p. Anybody would know what trick I can do to get around this? I'd love to apply, say P d by dp. But if I apply that, I'll get a kp. Oh, good. I'll still have a kp to the k, but then it's also going to hit the 1 minus p factor, and I don't want to deal with that. There's a nice trick you can do. Instead of using p and 1 minus p, what else could I use? Binomial theorem holds in greater generality. I could use p and q. It's still true. Can I still write p d by dp like this? No, what do I have to do now?
Partial.
I have to now use partials. So this is one of the reasons why this is a great topic to end the semester on. There's a lot of really nice ideas running through this. Frequently, the problem you're given is not the problem you should try to solve. Take a step back and put it in a broader context. Don't try to tackle it directly, but allow yourself the freedom of having a p and q. And now if I take the partial just with respect to p, everything's going to be nice here. And I'll get this expression over here now. And on this side, well, I now take the derivative with respect to p and I multiply by p, so I'll get an n p plus q to the n minus 1. And now set q equal to 1 minus p. And so we first do the calculation where q is general. And then at the end of the day, then we set q equals 1 minus p, and now we get the result we want. And this will give us the mean value of a binomial random variable. What's nice is this is a no-shit result. If you have a coin with probability p of heads, and you flip it n times, how many heads should you get on average?
N/2.
That's if it's a fair coin. It has probability p of being heads.
P times n.
Yeah, p times n. And so when q is 1 minus p, so if q equals 1 minus p, you just get np. So it's nice that it actually answers as you would expect. It does give the natural logical answer. And then you can use this to calculate the variance as well if you want to. So this is just meant to be an inkling of how useful this idea of differentiating identities. It is crucial in a lot of the questions we have in probability in terms of trying to understand distributions. By getting one identity in the beginning, we can milk it and get so many more. All right. Are we ready for the...
Yes.
All right. So recall the sum k goes from 0 to n of k is n plus 1 over 2. The sum k goes from 0 to n of k squared. Somebody correct me, it's n plus 1, 2n, is it minus 1?
Plus 1.
Or is it plus 1? Plus 1, okay. The way you check is just put in a specific value, 2n plus 1 over 6. And then there's other values as well. Did we talk about how to calculate the sum of the cubes nicely with the trick?
Yeah.
I thought we did that. And I thought I mentioned that I want to see if you can push that to get everything from just the first two. Okay, I thought we had talked about this. All right. But there is another way to prove these identities by using differentiating identities. This is probably the worst way to prove it, except for one fact. It is completely follow your nose. There is essentially no thought required. The quadratic formula is like that. Right? Negative b plus or minus square root of b squared minus 4ac over 2a. There's really no mystery in using the quadratic formula. Gee, I wonder what I should use for b. Oh, maybe that thing in the middle. Right? Yeah. There's not much. But when you try to factor by inspection, that can be much faster. But then you have the challenge of figuring out, well, what is the right thing? All right, so here's the start. 1 plus x squared plus x to the n. What does that equal? Almost.
1 plus x to the n plus 1.
Nope. Getting closer though. It's not 1 plus.
Oh, minus.
1 minus.
Sorry.
For what values of x does this hold? So for what values of x can I use this?
Greater than 1. More than 1.
Yeah, just not 1.
So I can use this for every value not 1? Okay, so far, every value except for 1 we're fine with this. The only value we're possibly concerned about is x equals 1. This is a huge advantage over the infinite geometric series formula. Why can we do this? Well, it's only a finite sum. Who thinks it works if x equals 1? So if x equals 1, what do you do? L'Hopital. You know you've made it when your name is a verb. Okay? You L'Hopital it. So you take the limit as x goes to 1 of 1 minus x to the n plus 1 over 1 minus x. This is of the form 0 over 0. So L'Hopital says if you have 0 over 0, then it's the same as the limit of their first derivatives. And if that's 0 over 0, do it again, right? So this would be the same as the limit as x goes to 1. Now we'll have a negative n plus 1 x to the n over negative 1. And that limit exists. The limit is just n plus 1. Which is exactly what we get because we're starting at 0. So we're going 1 plus 1 plus 1 plus 1 plus 1, n plus 1 times. So the formula holds for all values of n. We have actually just proven not the sum of k to the first or k to the second, but we've just shown the sum, k goes from 0 to n, of k to the 0 is n plus 1. Exciting. Through calculus. Okay? Why do you think I'm so excited? Yeah, we can generalize. I'm really not that interested in calculating the sum of, 0th powers of integers. I can calculate that very explicitly. But the sums of first powers, second powers, third powers, that's harder. What's the hardest part of using induction to prove this?
Knowing what the formula is?
Yeah, knowing what the formula is. If I give you the formula, if I'm generous, then induction is trivial. It's just, well, look, add the first n, take the last one, common denominators, and simplify. It's completely follow your nose. If I don't give you what they equal, however, it's very painful. Now, one way you could figure it out is you could make some guesses. If I want to sum, k goes from 0 to n of k to the p, this is approximately the integral from 0 to n of x to the p dx, which should be basically n to the p plus 1 over p plus 1. So you would expect that the main term is going to be n to 1 higher power. You expect the denominator is going to be 1 more than the power. And if you look over here, I'll have 2n cubed over 6, which is n cubed over 3. Nice and consistent. You would also expect that if n equals 0, the sum should be 0, as long as p is not 0. And so you would expect that there should be no constant term. So if you were to guess a polynomial, you would guess a polynomial of degree p plus 1. Here's the leading coefficient, no constant term. You could figure out what that polynomial is by just evaluating this for a couple of values of n. Take n equals 0, 1, 2, 3, 4, 5. If you do it for enough places, you now know the polynomial of degree p plus 1 has p plus 2 coefficients, but you actually know 2 of the coefficients, so you only need to evaluate like p minus 1 or something like that points. you could use that to sniff out the polynomial. And now that you have the polynomial, now you can prove by induction. So you can gather data, use the data to get the polynomial, and then prove that it works by induction. There are other ways to get to these polynomials. But I'm just telling you, here's one way by just doing some brute force. If you wanted to do 2018, it would not be pleasant, but it's doable. All right. What do you think we should do to both sides of this equation? What should we do to both sides of this equation? Or both sides of this equality? Take the derivative of both sides, right? This is the differentiating identities lecture. Differentiate is a really good choice. Take the derivative, apply x d by dx to both sides. So we want x d by dx, and here we have the sum. K goes from 0 to n of x to the k equals x d by dx of 1 minus x to the n plus 1 over 1 minus x. All right? So I get k x to the k minus 1. Okay, good. So we get the sum. K goes from 0 to n of k x to the k. And on this side, joy, I get the quotient rule. So I get a 1 minus x squared. I get the derivative of this, right, which will be negative n plus 1 x to the n times 1 minus x minus 1 minus x to the n plus 1 times the derivative of this, which is negative 1, so that becomes positive. So hopefully I didn't make a mistake.
On the left-hand side, has the kx to the k.
I take the derivative, so I get kx to the k minus 1, and then I multiply by the x, so I multiply back up.
Great. Fun. Good.
Okay? So does this look right? Hopefully I haven't made a mistake. Negative n plus 1, x to the n, 1 minus x. I think this looks right. Okay. What value of x do I want to evaluate both sides at? What value of x should I take?
1.
Yeah. So if I take x equals 1, what does this side become? It becomes the sum. K goes from 0 to n of k. If I take x equals 1, I'll get 0, and it'll be a second order 0 down below. I'll get a 0 over here. I'll get a 0 over here. So I get 0 over 0. So what do I need to do? L'Hopital. I take the limit as x goes to 1 of the above. Right, we've got 5 minutes left. That should hopefully be enough time to do the algebra. All right, so let's look at what we have. We have 1 minus x to the n plus 1 from this part over here. Then we have a minus n plus 1 x to the n, and the next here is going to be an x to the n plus 1. And then a minus becomes a plus. So I think it's going to become plus an x to the n plus 2 over 1 minus x squared. And we have 1 minus x to the n plus 1, a minus x to the n plus 1. So that looks like, I think that's going to just reinforce and become a minus 2 over here. I'm hoping people are watching the algebra. Does that look right? If not, we'll have problems. So we use L'Hopital, and we'll get a 2, 1 minus x down below. And now up top, when we take the derivative, this is fine. We'll get a negative n plus 2, and we'll get an n plus 1 from this. And then we'll have an x to the n, and then we'll have a plus n plus 2 x to the n plus 1. is. So it looks like we've made a mistake somewhere. Negative n plus 1 x to the n times 1 minus x plus 1 minus x to the n plus 1 times it is negative 1. Okay, so then we would have one minus x to the n plus 1, and then over here. Oh, we must have made an algebra mistake. So, is this correct over here? Do we take the derivative right?
Shouldn't the negative be for the 1 minus x to the n plus 1? I'm doing product rule with 1 minus x to the negative 1, right? So then that'd be negative 1, and then derivative of 1 minus x is 1 times 1 minus x to the n plus 1.
Am I getting the chain? Am I getting the quotient rule wrong? This is correct.
Yeah.
So the first term is I should have the derivative of 1 minus x. Oh, maybe I forgot to multiply this piece by x. That's what the issue was. We dropped that. All right, so let's see if we can do this really fast. We have negative n plus 1 x to the n plus 1. And then we have a minus, and a minus becomes a plus, x to the n plus 2. And then we have a plus x, and we have a minus x to the n plus 2 over 1 minus x squared. So now when we take one derivative, so here if we take x equals 1, we get 1 and 1 is 0.
Wait, why did you remove the negative n plus 1 for the second term of the
That's okay. I'm dropping the n plus 1 over here. There we go. All right, good. So now when we take x equals 1, we'll get 0 over 0. Good. We take the derivative, we get negative n plus 1, I think, squared x to the n plus n plus 1, n plus 2, x to the n plus 1, plus 1, minus n plus 2, x to the n plus 1, over 2, 1 minus x. When we take x equals 1, we have an n plus...
Shouldn't it be negative on both? No.
Yes.
What?
Yes. It won't matter because we have to take another derivative.
Oh.
But so if I make the mistake twice, I'm okay. But you're right, it should be negative. So if I now take x equals 1, we get n plus 2, n plus 1, n plus 2. So I can pull this out, and then this will become n plus 1 times n plus 1. So sadly, almost surely there might be an algebra mistake here. But if you keep doing it like this, you will see that you have 0 over 0. I'll send you the notes. And if you do it again, you will then actually get the formula for the sum of the first powers. You'll see how painful this is. You can do the sum of the second powers like this as well, or the third. For an A+, find a good way to do this for the general case. I will send notes on what I have on this. It's painful.